Hey, welcome back. I'm checking our stream. I think I got some better internet connection, so let's make sure that we're running. Sound seems okay. Cool. All right, so we're jumping into Module 3 homework. Module 3 is one of the hardest concepts and practical applications of so in general, this whole course is all kind of like scientific computing, taking engineering and scientific equations and figuring out how do I deal with this? Like, how do I get real numbers from this work? And really, if you were struggling with module 3, that makes sense because this is hard. And the work that I saw is really awesome, especially for most people. This is probably the first time you've ever thought about like using a computer to integrate differential equations and like think about engineering in this kind of abstract way of like, all right, how do I take this and turn it into a bunch of numbers and then take those numbers and plot them? So I think you're doing a really great job. So you should be very proud of the work that you turned in for this homework 3 because it looks good so far. I wanted to run through some of the deeper concepts here. I was thinking about skipping this then coming back, but for the most part it seemed like if people loaded in these projectile coordinates and it worked pretty well, but let's try it anyway. We'll go through one at a time, right? Main error that I saw pop up, well, not that one. If you actually run the first cell, this error kept coming up for people. And if this is if Python can't find a file, it's not that it really doesn't exist, it's that it's not exactly where you told it it was. So there's some troubleshooting that we can do. We can say like, all right, well, show me what files I have access to. And if I look in here, none of those files are projectile coordinates. And ls is like list files, and I'm using that exclamation point. So then I'll go one directory up and say like, okay, well, what's up there? There's that data folder again. And inside that data folder, in here is that projectile coords. So it should be there, right? So I'm gonna delete that one and say data projectile coords, and now it seemed like it worked. X comma Y. And the other thing that I noticed is that there might have been some issues doing that gap. The first step in this is creating a gap lines mean. So if we look at this part 1 reading, the very first step is coming down here, just measuring how many pixels 10 centimeters is. So we're like clicking on all these black horizontal lines and figuring out. And the number that I got was roughly like 52, I think 52 pixels. Yeah, coming in here. Oh, 53 pixels, at least when I did this. And you can watch Friday's video stream, or I opened up a GitHub discussions topic on it, but anyway, I won't go through all that again. So we have all that. We can do np.polyfit t and y and 2. So if I get a second order polynomial fit, this first term is my acceleration. If I think of this as like a projectile motion problem, then this one is my t squared term. So a over 2. So if I multiply that by 2, then the rough acceleration that I have from my clicking is going to be 10.2 meters per second squared. And again, anytime you're doing a fit, always plot your fit. So here's my coefficients, T and Y, T and NP dot poly val of PY and T. And now I've got my fit, the red line, versus the data, and sure enough, it looks like a good fit. I think that looks like a polynomial. That looks like a quadratic curve to me. But always, anytime you do a fit, always plot the data with your fit. It's just my. So this one, let's grab this. Let's say np dot load text. All right, cool. So we have I'm calling it HR for like high resolution. I'm taking column 0 over here, 0, 1, 2, putting that in my